Right, welcome everybody. This is 11.3. Hopefully you can see my screen. Now I'm going to flip through some of these pages and we'll probably do them in the lesson, but I want to focus on getting the explanations done on this video. So just a reminder then, at the beginning of next lesson, hopefully your lecturer will, definitely if it's me, maybe if it's Nick, ask you to make a list of the functional groups that you know. Now this table here, as a reminder, is really important because it shows you the functional groups in order of priority from least important to most important. By that I mean the stuff at the bottom, the ketones and the carboxylic acids, they always get to go at the end of a chemical name, whereas the functional groups towards the top tend to go as prefixes. So any halogens that are on a molecule are going to go at the beginning as fluoro, chloro, bromo, iodo. Alkene and alkane always will go at the end. And then these alcohols will either go at the end of a molecule if there's nothing else, there's no aldehyde, ketone or carboxylic acid present. However, if there is an aldehyde, ketone or carboxylic acid, you're going to get the hydroxy at the front of the name as a prefix. Why am I telling you that? I think it's important that you remember the order of all of these functional groups to help you to decide what gets priority at the end of the name and then what has to be shunted towards the front as a prefix. And remember, prefixes have to go in alphabetical order. For next lesson, make sure you've finished 11.2 in your booklet, and you might want to memorise the order of these. You do need to. Okay, so that will happen next lesson. Let's see what else we've got. Okay, so today's lesson is all about ways of representing molecules. Obviously, molecules are so tiny we can't see them, so we use symbolic formulae to represent them. Different ways of representing molecules will be more appropriate for different situations. So by the end of the lesson, what I want you to be able to tell me is empirical formulae, molecular formulae, general, displayed, structural and skeletal formulae. In this video, I'm going to talk through what each type is and how you work it out, and then you're going to have a go at the booklet questions ready for the lesson. So as usual, you're going to bring questions to the lesson. So the general formula is almost like an algebraic sort of equation that helps you figure out how many carbons, hydrogens and oxygens there are in any molecule of this specific homologous series. So for example, alkanes, you might remember from GCSE, the general formula for an alkane is CnH2n plus 2. For an alkene, because we are removing two hydrogens in order to form a carbon-carbon double bond, the formula is CnH2n. And for alcohols, what we've got is an oxygen in between a carbon and a hydrogen. So it's the same general formula as for alkanes, but CnH2n plus 2O. Or you can split that up and say, like it says here, CnH2n plus 1 OH. Pause the video and take a moment to just see that any one of these alcohols, you know, methanol, ethanol, propanol, butanol, all of them will fit this formula here. General formulae. You will be able to figure out general formulae for other functional groups by looking at what the atoms are in the functional group. Normally it's going to be, well, we'll give you some examples in the lesson. Displayed formula is where you've got the molecule and you're showing every single bond present. So often you'll see this written here as OH. It's really good if you can draw the bond between the oxygen and the hydrogen, so show all of the bonds. If you're going to have a double bond in a displayed formula, you show that as 2 lines, or a triple bond would be 3 lines. There's butane, and that one there, propan 1-ol. Now, empirical formulae, you might remember from module 2. The empirical formula, see if you can remember the definition, pause, and then play when you're ready. The definition of empirical formula is the simplest whole number of ratio of atoms of each element in a compound. And the molecular formula is the number of atoms of each element in a compound, or in a molecule, technically. So ethanoic acid, see if you can figure out what its molecular formula is. You know that it's got 2 carbons because it's ethanoic acid, and you know the structure of the carboxylic acid functional group is COOH. So hopefully you've got C2H4O2, and its empirical formula is going to be its simplest ratio of atoms. So can you simplify that at all? So you're going to get CH2O. That can't be simplified any further, so that's the empirical formula. What about C6H6? CH as the empirical formula. So pause the video and have a go at some of these. This is a throwback to module 2. I'm going to show you the worked example for question 1 on the board in a minute, and then any other issues you have, remember, message your teacher on Teams or bring it to the next lesson. Okay, so only listen to this once you've had a go at all of those questions. If you haven't, just rewind, have a go at those. They should be on page 20 of your booklet. And what I'm going to go and do is I'm going to get up and I'm going to write it on the electric whiteboard over here. You won't be able to see me for a minute, but you should be able to see me writing. Okay, so what you want to do, you want C, H, and we can write the percentage here. Percentage or mass goes at the top. So for carbon, we've got 81.81% carbon, and then we've got 18.18% hydrogen. And those are very pleasing numbers. And we want to calculate the moles for these. So you divide these by the MR. I have to go and get a calculator now. All right. So the moles of carbon is going to be 81.81 over 12. And that gives us 6.8175. And here we've got 18.18. Now this step here, don't forget this, we've got to now divide by the smallest. We're going to have 1 here, and then we're going to do 18.18 divided by 6.8175. And that gives us 2.6. Now that is a slightly awkward number. I think what we could do, we've got 2.6, it's times everything. Times everything by 3, and that should get us to the nearest whole number. So we have 3 there, 2.6 times by 3, going to be 7.99999, so 8 there. Okay, so then the empirical formula for this compound is C3H8. It's always a bit grim when we get something ending in 0.6 recurring or 0.3 recurring. If you've got 0.6 or something 0.3, you just need to times them by 3 to get them to the nearest whole number. If it ends in 0.5, times it by 2 to get it to the nearest whole number. And then if it's close enough, like to the nearest whole number, you can just round it up. Okay, so if you needed that help, there's one example done for you. Have a go at the others on page 20. Pause, carry on when you're ready. So have a go at this one as well ahead of next lesson. Use your chapter 2 booklet if you need a little bit of help with the formulae there. Enough said, there we go. So far you know what displayed formulae are, you know what molecular formulae are, and you know what empirical formulae are, and hopefully you remember and are happy calculating empirical formulae. So have a go at this review activity here, pause, and I will show you the answers when you're ready. So pause, play when you're ready. Okay, so display formula for 2-methyl-propan-2-ol. Always start with the stem. 1, 2, 3. Approach is 3 carbons long. On the second carbon, you've got an alcohol group, shown here by the 2-ol. And on the second carbon, you've also got a methyl group, which has shown all of the bonds You will see people doing like CH3 like that a lot, but let's do this displayed formulae really properly, show all the bonds. There we go. Next one, the molecular formula. You should have got, let's see, so we've got 4 carbons, C4H, now we've got 3, 6, 9, C4H9, and then OH. If you put C4H10, O, that's also good. And then the empirical formula, see if you can simplify this at all. So we've only got 1 oxygen present. We can't halve that, can we? So the empirical formula is also the molecular formula. Time for structural formula. This one's new. A lot of you have been really good at sort of figuring these things out using the evidence we've got, but explicitly then, structural formula, I guess, is like displayed formula minus any bonds. So displayed formula is just something that shows all of the bonds. Structural formula, we'll get rid of them. So there's the displayed formula there for propane and for 1-bromopropane. The structural formulae will collapse that into one line that you can sort of, I guess you can just type it on a line, you can write it on a line. So there you go. The structural formula for propane is CH3, because you've got this. That's drawing, wasn't expecting that. You've got that one, CH3, CH2, CH3. Lots of you will have had some experience of this from doing 11.2 in your booklet. See if you can do 1-bromopropane. Pause me, play when you're ready. So 1-bromopropane, CH3, CH2, CH2, and then Br at the end. If you have branches, put the branch in brackets. So here, structural formula, see if you can figure it out. I have CH3, and we've got CH2, but on this carbon, you've got this methyl branch. So then this methyl branch goes in brackets, whoop, just like that. And then you've got the CH3 there. See if you can name it, pause, carry on when you're ready. So you've got methyl group on the second carbon. Do the stem first, prop. No other functional groups, so propane, and then put that branch on the front there, 2-methyl-propane. Some of my first years in today's lesson have figured this out already. There's the structural formula for decanoic acid. Can you think of a way that you might squish that down to make it even simpler? Because we're just trying to save time here. Give you a hint, it includes brackets. Okay, so what you're going to do, CH3, and then grab all of these CH2s here and just squish them into one bracket. So we've got 1, 2, 3, 4, 5, 6, 7, 8 CH2s. So we can just go get all of those and just put them like that. And then you've got COOH, which is how we're going to show a carboxylic acid in structural formulae form. Skeletal formulae, they're the ones that you've seen everywhere. Finally, everything that you Google will make sense, hopefully. So skeletal formulae are the easiest. Once you've got the hang of it, it will save you so much time. You'll be so relieved not to have to draw thousands of hydrogen atoms anymore. So here you go. All you do is, if there's nothing else going on, you just draw a zigzag line. At the end of each line is a carbon atom. Every time the line changes direction, you also get a carbon atom. Organic chemists know what is supposed to be going on with the hydrogens. They don't need to be told every single time. You know that if a carbon is on the end of the molecule, if nothing else is going on, no other functional groups, then that carbon has got room for 3 hydrogens. So these ones here will have 3 hydrogens. Everything in the middle here, so this carbon has got 1, 2 bonds to other carbons, so it's got room for 1, 2 hydrogens. Likewise here, here, and here. Okay, so we just don't draw the hydrogens on the skeletal formulae. My advice to you is when you've done a big zigzag, especially if it's a long chain, go back and count the carbons again. It's really easy to make mistakes and your zigzag be too long. So 1, 2, 3, 4, 5, 6, and we've got 2, 4, 6 carbons here. Fine. Okay, now if you've got branches, this is what you do. So you've got your zigzags, and you'll get used to how they look. That's pentane. If you've got 3-methylpentane just here, do your zigzag. So same as naming, really. Identifying along this carbon chain, draw that. And then you can start to add all of the functional groups and branches that are coming off it. So on the third carbon, 1, 2. I'm doing this with a mouse pad, so that's why the handwriting is terrible. There you go. 1, 2, 3, or 1, 2, 3 in the other direction. On the third carbon, you just draw a line to represent this CH3 group here. Cyclical compounds, you just sort of, you're deleting all the carbon and hydrogen bonds, aren't you? Delete the carbon atoms, delete the hydrogen atoms, draw what's left. So here you can see we've got 5 carbons in a ring, so we're going to have a pentagon. Here we've got 6 carbons in a ring, so we're going to have a hexagon. And to show the double bond in a skeletal formulae, in any kind of molecule, just draw a double bond like that. Benzene is something that you are going to do next year. It's a bit mad the way it reacts. There are 2 ways of drawing it. I guess technically the circle is much more accurate, but we won't go into that now. These compounds, anything that you see that has this structure or this structure, they're the same effectively. They're called aromatic. So you should have learned aliphatic, being straight chain carbon compounds, alicyclic, which is where a carbon chain is joined together in a ring. This is kind of the third category. This is compounds that contain 1 or more benzene rings. And that's how you draw it skeletally. Okay. Hopefully you can know what these hopefully you know what these parallel lines are. They are double bonds. So just draw 2 lines for a double bond. And that's an alkene. And at either end of the double bond, just be careful. This is where mistakes can be made. If you have a look here, maybe I'll draw over it in red. This carbon, this one just here on this corner, has got 1, 2, 3 bonds to it. So it's only got room for 1 more hydrogen. Just bear that in mind. Okay. Yeah, so when you're counting the carbons in a molecule, you want the numbers to be as low as possible, unless there's a high priority functional group, in which case count from the end of the molecule that's got that on it. But here we could do 1, 2, 3 and have pent-2-ene, or we could count the other direction, so we could have it as pent-3-ene, 1, 2, 3. Okay, but 2 is obviously the lower number, go with that. There you go, butan-2-ol. So we've got an alcohol functional group. And the way you draw that skeletally is you draw a line from the carbon to the oxygen hydroxy group here. The misconception, the mistake that students are likely to make is thinking that at the end of this line here, this one here, that there's a carbon. There is not. There are 1, 2, 3, 4 carbons in this molecule. There is no carbon here. Okay, that is just a carbon-oxygen bond. Okay, pentanoic acid. This is how you show carboxylic acid on a skeletal formulae. So you've got, again, the last carbon of this chain just appears here. There is no carbon at this end. There is no carbon at this end. So we've got a carbon double bonded to an oxygen here. It's called a carbonyl. And then we've got the carbon singly bonded to our hydroxy group here. Now, when you have a carbonyl and a hydroxy group on 1 carbon atom, that's called a carboxylic acid. Okay, see if you can get the structural formula. Pause the video, play it when you're ready. Okay, functional group, carboxylic acid. Structural formula is going to be CH3, CH2, 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 COOH. Or you can bunch them together like this if you're being pro. Okay. Yeah, and then as we were saying, I don't know whether the numbers, no numbers. As we were saying, you want a number. So if there's anything else going on this molecule, you'd need to number carbon chain from the end where the carboxylic acid is, like so. Okay, here's some more complex ones. what I think you should do now is identify the functional groups. Okay, identify the functional groups, draw them out as displayed formulae or as structural formulae with benzene rings. You just want to do C6H, and then there's 1, 2, 3, C6H3 here, and then have these coming off it. There is one functional group here, two functional groups here that you haven't come across last lesson. So there's benzene, that's a carbonyl, and we've got an amine, and that red thing there, I'm sorry that I can't get this, cannot get the home screen gone, but this red thing here is called an amide. Let's try and write that in my, look at this handwriting. Amide, that's a D by the way. So the red circle is an amide. Biologists, this is what we get between amino acids when we make proteins, amide links. All right, there you go. So I'd like you to have a go at 11.3 in your booklet. If there's any confusion about what I've said, maybe play me at 0.75 speed, or rewind, or watch Dr. Beatty's Chemistry Essentials. You want to go over this again. And message me any questions, bring the questions to the lesson. Thank you for listening.